Okay, so our next speaker is going to be Matt Walter, who is an associate professor at TTIC, or the Toyota Technological Institute of Chicago. And he's also affiliated with the University of Chicago. He directs the Robot Intelligence Through Perception Laboratory, and does some great work using machine learning to enhance robot perception and intelligence in unstructured environments. And his work has been recognized by multiple awards, including the NeurIPS Best Paper Award. So let's welcome our speaker.
Thank you. Thank you. I think, just to be fair, I think the NeurIPS was, I think it was a workshop. So just, I'm not over claiming. So thanks. This is going to be very much an applied talk. One of the good things about robotics is you get to show a lot of videos. So you'll see a lot of videos. And so this work itself that I'm talking about really is led by Takuma Yoneda, who's now graduating. Unfortunately, he's more interested in maybe making money and going to industry than going to academia. And then other folks, so one Bradley Sadie at Northwestern, Guy at MIT, and then Lucha's a new student now at TTIC. Okay, and so I've been a roboticist for a while, and we've seen with our our ability, particularly with machine learning, but more generally our ability to mitigate uncertainty, we've seen pretty tremendous advances. I'm sure everyone here has seen on YouTube videos of Boston Dynamics. So it's pretty amazing what Boston Dynamics can do. It's not clear how much learning historically they've been doing, I think more so recently, but it's still pretty amazing what they can do. And we all know applications of self-driving. So really settings where we can see autonomy in the real world, not just in manufacturing settings, but in real world settings. Primarily, this is in the context of settings like navigation, maybe legged locomotion, less or so when we're interacting with the environment. So we can act in the environment, we can do that autonomously, mitigate uncertainty. When we're interacting with the environment, like manipulation, autonomy is far less capable. It does succeed when the environment is fairly structured and the tasks are fairly structured. And so these are just two recent videos. The most recent one, I think this came up a couple weeks ago, this great platform, Aloha, for collecting demonstrations with something like kinesthetic teaching that you might be able to use to train a model. Many of these tasks, many of what you're seeing, I think, are actually being demonstrated. They're not autonomous, but what they can do autonomously is still pretty impressive. But we're still limited in terms of what we can do with autonomy. And so the work that I'm going to talk about today has been inspired by this NSF-funded project for underwater manipulation. And so this is a video from, I think this is off of Santorini in Greece. So these are hydrothermal vents, and we want to do some sampling of these hydrothermal vents. So these very unstructured environments where we want to be able to interact, not just map the seafloor. EOD disposal is another setting where we want to do this autonomously. In all these settings, none of this is autonomous. They're all controlled by people. So in the case of this manipulator arm on this robot Nui, there's a person or many people in this control van with a dozen monitors staring at data fed back from this robot that is 500 meters below the sea surface. In this case, joysticking the arm. Same thing with the EOD disposal. Assistive technology. We have this user of this Jayco arm, and now retrieving, I think, his juice from the refrigerator. I don't know if you saw it in the clip, but he's controlling the end effector using his foot. So again, teleoperating in this arguably more structured setting. And we see this in a number of domains where autonomy is not yet there to be able to do this entirely autonomously. And so we would like to be able to do is sort of bridge this gap between, in this case, really glorified RC cars and full autonomy, be somewhere in between. And so to motivate this, again, I'm going to show this video, or picture rather. This is Nui, Nereid Under the Ice, a pretty awesome platform developed by the Woods Hole Oceanographic Institution. So there's a small car-sized, what they call HROV. So it's a hybrid ROV, or remotely operated vehicle, or autonomous underwater vehicle with these doors in the front. They open up and there's a manipulator in there and cameras. Again, a pretty amazing platform designed to operate under ice sheets. So the vehicle trails this hair-thin umbilical cord for data, not power. It's 40 kilometers in this coffee can, so it can go underneath the ice. And so it's connected to this ship. So on the ship, you have a very high bandwidth connection to this robot, and you can afford, despite the fact that it might be several kilometers away, I think the depth ratings maybe it's 8,000 meters or so, joystick this arm with very high bandwidth, low latency. What we would like to do, and this is again this NSF and NASA funded project, is to not require someone to be controlling this vehicle on the ship, but be able to control sampling, intervention with the underwater environment from thousands of kilometers away in your home or in your office. And so we had a proof of concept of this where we did exactly that. So we had someone, so the vehicle was off of LA. I was on the ship, there are a couple other people on the ship, but there was someone in Chicago, one of my students, someone in Woods Hole Oceanographic, this is a collaboration with them, someone in Boston, controlling this vehicle, and it was, I think, 1,000 meters below the sea surface, collecting data by controlling the arm. And so something where, over satellite, so very low bandwidth, high latency, we cannot teleoperate this. So we want is somewhere that sits in between this full autonomy and full teleoperation, where we would like the user to be able to maintain some level of control authority. And this is important in assistive technology settings, where you want to feel like you're in command of the robot, of the arm, but you cannot afford, for various reasons, to be teleoperating it. So we want to sit somewhere in between. Okay, this is something we've been working on for a while. This is referred to as shared autonomy, and people have been looking at this for decades. And that high-level idea is that there are tasks that people are good at doing, like reasoning, scene understanding, that robots are not. Maybe, with the use of language models, robots are becoming more and more capable, at least in terms of reasoning capabilities. Robots are good at doing what's called inverse kinematics. So I want the end effector to be here, solving for each of the joints in the arm to get the arm there. People are not. So the idea with shared autonomy is, can we ideally have the robot do what it's good at, and the human do what they're good at? And so you get this diagram, this robot picking fruit, and you have this human providing some input that's AT to this robotic or this agent, and then that's going to be controlling this system. And really with shared autonomy, the trick is, how you actually determine this action that's executing on the robot based upon this input provided by the human, right? And people have been doing this for decades. Typically, what people will do is formulate this as two different sub-problems. One is, how do we predict the user's intent? What does the person want to do? Do they want to pick up the grapes? Do they want to pick up the orange? Do they want to pick up the apple? Maybe we assume that the intent is known in the beginning. Or we assume that the intent may not be known, but there are only 3 objects that I can pick up, and now I want to do inference over that goal. So I have these noisy observations of what the user is doing with the joystick commands. From that, can I infer what their goal is? And once we get the goal, we can then go manipulate that object. So that's what, up until recently, all the methods have assumed, and maybe a model of the dynamics as well. What we're interested in is relaxing these assumptions. So where we don't know, the goals may not be discrete. They may not be, we assume they're not known a priori. We don't know what the user's policy is. And we don't know the model of the environment. Can we still provide some effective shared autonomy approach? And we don't get any feedback from the user. So they don't give us a reward when we did it well. We don't know the task. So we don't have a task reward, which, if you have, it makes this problem easier. We want to relax that, assume that we don't. So we don't know what the user's intent is. We don't even know the set from which it's drawn. We don't know their policy, but we will assume we have some demonstrations. Here's how people would perform this task if they had full capabilities. So we have some demonstrations of this. Okay. So let's look at this pictorially. So we have this distribution over actions. This is a state condition distribution. So ST is the state of the world. This might be an image plus the configuration of the robot arm. And there's this distribution over actions. So let's assume we're able to learn this distribution. So in this cartoon example, each one of these actions might correspond to picking up a different piece of fruit. Or they might, as I'll show later, if we're flying a drone, they might correspond to different ways of flying the drone. Or if you're driving a car, this one might be people who like to drive very cautiously. This people who like, speed, et cetera. And we have some user who's providing some input to this system based upon these states, and they're far less capable. So they might have some actions over here that are going to cause the arm to crash into the table, or in the underwater environment, the arm to crash into the seafloor. If this is a manned submersible, maybe hit the glass that's protecting the people inside from the outside environment. So things that might be dangerous. And so what we are interested in doing is taking this observation, this sample of what the user decided to do with this joystick, which again is noisy, possibly unsafe. And we like to figure out how to map it to what is a safe, effective action to take based upon that state conditioning. And ideally, we want to do this in a way that allows them to preserve some level of control authority. And so how might we do that? If we have access to demonstrations, could we learn to do this mapping from this user level input to this optimal distribution. And so for that purpose, we're going to use a generative model. So we want to generate actions that are consistent with that expert distribution while also giving the user some level of control authority. So let's say, just a brief, summary of generative models, and particularly diffusion models, which is what we're using. And I imagine most, if not everyone here, is familiar with that. Say we want to generate pictures of dogs. So there is some data distribution that underlies what dogs look like, and we'd like to be able to sample from this. I want to be able to produce, arbitrary images of dogs that may not exist in reality. So what I want to do is then I'm going to take some examples. I have, tens of thousands, 100,000, millions of pictures of dogs, and I'd like to learn some distribution over those images such that I can then sample from that distribution to produce my images. Maybe you want to do it with cats if you're a cat person. Same idea, right? So for this purpose, again, we're going to use a generative model known as a diffusion model. And a diffusion model is it's gained popularity in the last several years, but not so new generative model that has its origins in equilibrium statistical physics. And the basic idea is that exactly that. It's pretty simple. So we have some data distribution Q that we don't know. And I want to be able to learn to model P such that when I sample from it, I can generate a sample that's consistent with this data distribution. So the way that I'm going to do that is I'm going to basically destroy structure that exists in this data distribution, so noise it, then learn to denoise it. And so we're going to do that in two steps. One is going to be this forward, so both diffusion processes. One is this forward diffusion step, where we're going to take a sample from our data, and I'm going to noise it. So let's say now it's not dogs, it's a picture of a face. And this is from the Ho and others paper. So I have a picture of a face. So now that's what I would like to do, generate pictures of faces, realistic faces. So this is it from my data distribution, or from my data. And I'm going to gradually add noise. And I have this Markov chain that's going to be doing this. And I'm adding Gaussian noise at each step until I get, in the end, a uniform Gaussian distribution over this space. And really the art comes in this reverse diffusion process, where I'm going to train a model to be able to reverse this forward process that's adding noise. So that really in the end, what I can do if I want to generate a picture of a face, I sample from a zero mean Gaussian, and then I apply this reverse diffusion process to denoise it to get a sample from my data distribution. And again, this is also a Markov chain. And really the key is in this reverse diffusion process. Okay, so that's how this works. Now, if you imagine doing this for shared autonomy now, what you might imagine doing is that, we want to generate nominally, if we generate a face now or a dog, is maybe an action drawn from this expert distribution, this data distribution. We have these demonstrations of how an expert might play this game, how they might fly a drone, how they might manipulate things in the environment. Well, if we think of this using a diffusion model, what I would do is I would sample a zero mean Gaussian from a zero mean Gaussian, apply reverse diffusion, and I get a sample from this distribution of our expert actions. But if I do that, I've completely lost the user's intent. The user has no level of control anymore. So that's sort of, if I'm, full diffusion is over here. I've just ignored what the users wanted to do, but I've gotten a good, by some definition of good, an action that's consistent with this expert distribution. At the other extreme, if I don't do this, I might just apply what the user did, execute that on my robot arm. But there's the possibility that at the very least it's suboptimal, but it may not be safe. The actions are quote unquote bad. So what we'd like to be able to do is sit somewhere in between, where we get actions that are as close as possible to the data distribution, while also not deviating too far from, and we can quantify this, too far from what the user's actions were. Okay, so let's look at this. So nominally what we might do is I might sample from zero mean Gaussian noise, I apply my reverse process, and I might get a sample from over here, something from my expert distribution. So if I were to apply this, I have the user's action is somewhere in the upper left, noisy, not very good. I might run the forward process, get zero mean Gaussian noise, the full forward process. And basically, once I've done this, I've lost all signal that might be useful in inferring the user's intent, then work backwards. What we do is pretty simple. And we have this switching time. So basically what we do is we do this partial forward and reverse diffusion. So rather than take the user's action and fully run our full forward process to completely noise it and then reverse it, we go part way. So we add a little bit of noise to the user's action, but not all the way to a zero mean Gaussian. And then we apply our learned reverse process. And then we, the extent to which we go forward and then reverse is this K switching time. So that's the basic idea, and we can show that how much we deviate from the user's action. So that gives us a control, like a knob that we can tune if we want to. Around the same time, there's this great paper by Ehrman's group, SD-Edit, where they have a similar idea. And so in this example, it's not shared autonomy anymore, but the idea is I want to generate a picture. Let's say I want to generate pictures of castles. But I want to be able to provide some context. I want to guide the generation in some sense. And so what I might do is I might sketch what I want the image to look like. So I want to generate an image that really looks like it's a castle, but it's consistent with what I've drawn. So if you imagine these as being distributions, I have my distribution over images here. These are images of castles. I have my distribution over these sketches, these strokes. And these distributions are very far apart. There's no support. So what we're going to do, or what they do, again, it's very similar to what we do, is that you can imagine taking these two distributions, you add a bunch of noise. Now that there's some overlap, and then you apply the reverse SD, this reverse diffusion process. So you have your stroke here. This is my sketch of a castle. I add some noise, and then I apply my reverse process to get an image that's looks like a castle, realistic image. So it's from this data distribution of images, but has this context that I provided in the form of this sketch. So that's basically the idea we're doing here. In our case, there's no stroke, but the stroke is the user's input with the joystick or whatever the different control input is. And then the castle image now is actually controlling the arm. Okay. And so we've done this in a variety of simulated, and I'll show real quickly some real world settings where we do this for manipulation. These are sort of benchmark tasks that people have used for shared autonomy. One, if anyone here has played Atari, Lunar Lander is one, or if anyone's played it, it's, at least for me, very difficult. But the goal here is you have this drone, you're trying to fly it to land between this flag, and the flag's position moves each time you play the game. And you don't want to, you don't want to crash, you don't want to go off the screen or the game's over. And it's really hard. Lunar Reacher is a variant of this that we came up with in another paper, where the goal is you have some goal, this location in the environment pops up somewhere, and the goal is to fly to it. And so we collect some demonstrations, and in this case, again, if you imagine those three clusters, one cluster might be landing in the goal. Another cluster, some people might just like to fly around the environment. Another one might be to land in a different location, maybe. And the other one is block push, where you're told, the user joysticking, controlling is told to push this block in one of these locations. Now, the shared autonomy algorithm doesn't know what the goal is. It can't see the flags where the landing zone is. It can't see the goal where you're supposed to push the block to, et cetera. So we showed some video here. We evaluate different types of pilots, humans as well as surrogate humans. These are noisy and laggy pilots. And then we look at, so this is just video is showing with and without we call it a co-pilot, with or without our our partial diffusion-based shared autonomy algorithm. We look at things like how successful was it in completing the task. So higher is better. So if we look at these different pilots, when we turn on our co-pilot, our assistants, the success rate increases significantly. When the crash rate, you want to be low, of course. When you turn on our co-pilot, the crash rate decreases significantly. So again, it's a pretty hard game to play. And I should say, again, there's this idea of how much forward and reverse diffusion do, that K that you do. And we found, and again, I don't have, it's in the paper, this is at RSS this past year, robotics conference, that it's there's a sweet spot. So this gamma or K of 0.4 seems to work across a variety of domains. Okay, so I have 1 minute left. And so we do this for pushing. So this is just showing, anyway, I can, for the sake of time, I'll skip over this. We actually did this with humans as well, had them play this game. We also did this again. Ideally, we'd like to run this in the underwater environment for various reasons. we have not. So we've done, a version of this in our lab. So this is like something like the Towers of Hanoi, if you ever played that. You're told to put this, in this case is electrical tape, on one of these rings. And you're joysticking, you're looking at this video feed, like you might do on a ship, controlling this arm. And with and without our shared autonomy. I think the video will play here. So we see that people by far, we ask them, just provide some feedback. They prefer by far using our assistant versus no assistant. They're far more successful at the tasks, or at least it takes them much less time. We actually let them do it as long as they wanted. Anyway, so that's that. I think I'm out of time. So that's the RSS paper. Some other papers related to this that we've been doing for shared autonomy and diffusion models for robot planning. So.
All right, thank you, Matt. Do we have any questions? Yeah.
So in the case of this, like assisted that like controlling some robots, like you need to do this in real time. It's not the same as generating a castle. It's like in the application, like in applying this algorithm to like the setting of like some robotics, you have to like compute this in real time, like the noise. So is that like not an issue?
No, in these settings we're doing this in real time. Now the state space we're doing this in relative time, so that makes us more tractable. But in these domains we're doing that in real time.
Thanks.
All right. Do we have any other questions? Yes.
Is there an approach that would work by optimal transport between like the user, the expert distribution, and the user distribution while we try to?
Yeah, that's a good analogy. I'm not aware if I've done that, but I imagine that you could, right? Because that's what it looks very much like in the picture that I show is transport. Yeah.
Cool. Any other questions? All right, let's thank our speaker again.